Hi there. Today we're looking at implicit neural representations with periodic activation functions by Vincent Sitzman, Julian N.P. Martel, Alexander W. Bergman, David B. Lundell, and Gordon Wettstein. So this paper is a bit of a special paper. If you're like me, coming from like classic machine learning or deep learning, things like this paper requires you to think around your notion of what it means to handle data and so on a bit, and to think about data points and so on. Essentially what they're doing is they are representing signals such as images or sound or generally waves or point clouds. They're representing these signals as functions mapping, for example, from their coordinates to their values, and we'll see what that entails. And they're not the first ones to do this, but they managed to do this very well using these new models called Sirens, which are basically neural networks that, so Siren spelled like this, neural networks that have sine waves as their nonlinearities instead of like ReLUs or hyperbolic tangents and so on. So it turns out that if you initialize these very carefully, those can be made to capture these signals very, very well. So that's the kind of high-level overview, and we'll go through the paper in a bit of a fashion of someone that is not in this particular literature. So this is not going to be like as in-depth or technical as usually, because I myself am not super familiar with this kind of literature, with the neural representations and so on. So if you go at this paper from a machine learning perspective, the first, like you're going to be ultimately like super confused at the beginning. So I'm going to try to kind of clear up, retrace my steps of my confusion. Okay, so I love that this paper starts out at, we are interested in a class of functions phi that satisfy equations of the form this right here. Like, aren't we all like we are interested in a class of functions? Okay. I've never, particularly had many dreams about functions like this, but so how can you look at this? So we're interested in the relation between inputs and outputs. This here is the function, as you can see. This maps input to output, okay? And we're also interested in its derivatives. So here you go first, second, third derivative, and so on. So this function right here is what we're going to call a neural representation, or an implicit representation. It's called a neural representation, I guess, if it's a neural network that this function is. So far, so good. You've seen this, right? You've seen this could be a data point and then could map it to a label or something like this. Since we're going to represent images, you already know maybe a GANs, a generative adversarial network, where this here is the latent vector, and then you have a neural network mapping this latent vector to an image, right? So this is going to produce an image. This here is quite similar, but not quite. So in a GAN, I guess this here would count as the representation, the continuous representation of this picture. However, in this case right here, the function itself is the representation. So in a GAN, what we do, we learn this right here, this function phi. We learn this from data, such that if I plug in one particular vector, I get one particular image. And if I plug in another vector, I get another image. And the function always stays the same. Here, it's going to be one function per image. So each image, the function is the image. So how is a function an image? You can simply, if I have an image and it's made of pixels, right? So it's made of pixels. Each pixel has an x and a y coordinate, okay? Let's call that x1 and x2 the coordinate of that. And each pixel also has a color value, right, which is three-dimensional. So each pixel has a three-dimensional RGB color value. So technically an image is a function from coordinates to pixel values. Okay, so if this is my image is represented by a function, then if I input any coordinates like 3, 4, that function should return what are the RGB values at that. Maybe it's like 0.5, 0.7, and 0.1. Those are the RGB values at that. Okay, so now the goal is to have this right here be a neural network where I have like a multi-layer perceptron, and I think they always use like a 5-layer MLPs, so really simple neural networks, and you simply input. So here you have 2 input neurons where this here goes, so one gets the 3, one gets the 4, then this travels through the network, and at the end the network should output 3 output nodes, and these should be like the 0.5, 0.7, 0.1. Okay, now again, this network here is, they now train this network to map input to output, okay, to map coordinates to values. And this, of course, it is one particular image, so you're going to have one neural network per image. Now, you might reasonably ask, why do we do it like this, right? Why don't we just save the image as the pixel values? Why do we need like a function mapping the coordinates to the pixels? And that's a valid question, I guess, and the image is just one example of this. But one advantage that you immediately get is that now you have a continuous representation. So now you cannot, not only do you know, because if you store an image like this, you only know its value at each of the pixel locations. However, if you store an image like this, you know its value at any continuous in-between location, right? So you can ask the network, what's the pixel value at 3.2 and 4.1, right? It will give you an answer. And if the network is trained well, it will give you sort of an answer that makes sense. That is, what's the exact color at this sub-pixel location right here. Now, so far so good, right? So essentially, this boils down to not really a machine learning problem in the classic sense, but an optimization problem, because all you have to do is you have to make the neural network match all input to all output. There's not really a training and a test set right here. Namely, your data set is going to be all the pixels in the image. So each pixel in the image is going to be one data point, because it's one. So each pixel is XY to RGB. Okay, and the way they train these networks, now at the examples of pixels, the way they train it, they simply sample a mini batch of pixels, like this one, this one, this one, this one, this one. They use that mini batch to train the network, to do one step to train the network, and then they sample another mini batch and so on. You might sample the same pixels multiple times, but ultimately what you want is sort of a continuous representation of the image. That this is not a new idea, this has been around, and they cite a lot of literature where this has been around before. So what their new thing is that they say these other representations, so if you use a neural network in a classic sense like this, and you do your training with the mini batches like this, what you'll end up with is a bad image. So if you then simply go, right, once you've trained the network, you can take your network, and you can simply output each pixel location. So you say, okay, now I'm going to reproduce this image using my network, because if it had trained well, it could certainly give me back the positions at the pixels, right? So you ask it, what's a 0, 0? What's a 0, 1? What's a 0, 2? What's 0 at 0, 3? And you can fill in the picture, and that usually gives you very bad outcomes, or so they claim. I mean, I haven't checked it particularly, but you can see right here, this is the ground truth, and here you have a network that is parameterized with ReLU functions, like with ReLU nonlinearities. And as you can see, the ReLU network misses a lot of the sort of higher definition things in the image. And so it depends on the architecture that you use, how well you can make a neural network represent those things. Again, you kind of need to forget what you know about machine learning in the classic sense, because like I'd still see people here going like, "Ooh, just use a GAN or something like this." So yes, valid point, but we're in the business right now of solving this particular problem. And as we'll go on to see, it's not just about images. But images are a nice example of a natural signal. So the TAN-H networks, you also see, I think they fail even harder. They have these artifacts back here even. And this here, it gets better when you do ReLU networks with what is called a positional encoding. So not only do you have your X and your Y coordinates go through a ReLU network, but you also have them go through a positional encoding. And that's very much like you would have in a transformer. So if you watch my video about attention is all you need, I explain how the positional encodings work there. But basically what you do is you map these things to cosine and sine waves. So you're going to be like the sine of X times 10, and then the sine wave of X times 100, and so on. So which you'll end up, and you do the same for Y, and that ends you up with more features that sort of then the function can use to represent positions way better than just given the X and Y coordinates. If you do that, you kind of recover some of the image, but you see here they also analyze how. So this is the ground truth, and this is the gradient of the ground truth, which is basically a Sobel filter, if you know that. It's basically an edge detector color gradient thing. And then this here is the second derivative, the Laplacian of the image. And ideally, if your implicit representation models the signal very well, it should also model the derivatives of the signal very well. So now we're kind of connecting it to what we saw at the beginning, right? These Siren networks are specifically designed to not only match the signal right here, but also match its derivatives. And if you match, maybe in an image it's not that important to match the derivatives, even though it is, because there are small things, like you can see right here, the grass isn't as well represented, and here you get some artifacts that you see here in the gradient. Might not be as important for images in terms of human vision, but for many signals it's also important to match the derivatives. And here the Siren, even though it's trained on the image itself, you can see that its derivatives are very much in line with the original signal. So simply by matching the signal, this architecture manages to also capture the derivatives of the signal and therefore have a more faithful representation. Okay, so that was positional. RBF ReLUs are simply the ReLU network, and I think somewhere in here there is an RBF kernel. If you young kids don't know what an RBF kernel is, then yeah. No, I guess I don't wanna dunk on anyone. It's basically how do I explain it? You map it to an infinite dimensional space using Gaussian kernels. Yeah, maybe Wikipedia is better at that than I am. So, Sirens, what do they do in order to be able to capture a signal very well? How is a Siren different from like an RBF network? And the answer is pretty simple. So the architecture of a Siren network is the N. Does it already stand for network? I'm not sure, honestly. Maybe we'll find out. Yes, it's dubbed sinusoidal representation networks. So the N is network, so we don't say Siren network, we say Siren. And a siren is simply made of, what is that? Here, it's a multi-layer perceptron, basically, right? So it is this here is the network. The network, this is the final layer of the network, which is a linear layer. Before that, you have all these layers just not concatenated, but following each other. So it's a multi-layer perceptron, pretty regular, and each of the layers in the multi-layer perceptron is made up like this. You have an input, you multiply it by a weight matrix, you add a bias, and then you put it through a sine wave. So the sine wave here is really, that's the only change from a MLP otherwise. So usually here you have something like a sigmoid or a ReLU function. Now you have a sine wave. And it's a bit weird, right? Because a ReLU function is like this. So it has this center thing where it kind of switches, but here it's linear and monotonic, and here it's kind of constant. And even a sigmoid. So the sigmoid is, I don't even remember, like this. Yes, I guess. So the sigmoid is like this. So it's kind of constant here, monotonic, and so on. We're used to monotonic activation functions, whereas a sine wave is really different. The sine wave, of course, is something like this, right? Where it's not monotonic at all. Like if you want to increase your function value at any point, and you're here and you go up the hill and you do a step that's too large, you end up down the hill again. But it turns out that these networks have particularly have some good properties if you want to capture natural signals, and they have some bad properties, namely that the fact that they are periodic and go down again. And the reason why they get around the bad properties is because, or so they claim, they initialize the network in a very particular fashion. Because I think, at least when I started in deep learning, I had this idea, so a lot of other people must have had this idea too, of like, hey, what if I just replaced nonlinearity with like a sine function? Could I do something like this? And then tried it out, and it didn't really work, so I scrapped that. Now this here, of course, isn't simply replacing the neural network. It's also using the neural network for something completely different than I would. Namely, it's using the neural network to learn these implicit representations, and not like I would to do simply for learning a data set. But still, it seems like you need to initialize them fairly with very careful consideration, and we'll go on to that right now. So actually they just describe it. It's not very interesting, but you need to sample the weights uniformly from this uniform distribution, where I think, yeah, and they have a proof in the supplementary material where they sort of show why that is. So, or not, here we propose to draw weights with C equals 6 such that W is in this uniform distribution right here. Oh no, it's different. Okay. This ensures that the input to each of the sine activation is normal distributed with a standard deviation of 1. Since only a few weights have magnitude larger than pi, the frequency throughout the sine network grows only slowly. Finally, we propose to initialize the first layer of the sine network with weights so that the sine function spans multiple periods over -1 to 1. We found W0 to equals 30 to work well for all the applications in this work. The proposed initialization scheme yielded fast and robust convergence using the atom optimizer for all experiments in this work. So the initialization here takes a fairly prominent piece in that paper, which tells me maybe that they have spent a lot of time working on this. And this is, I mean, if this is the case, this is to their credit, because I guess most people like me would try out something like this and then after a while realize it doesn't work. And to, be so convinced to go and really figure out how do we need to initialize these to make it work. And of course, as you're doing this, there's still like a 99% chance that it's not going to work once you've done that, is quite respectable, I find. It might have been really different. This might have been the first thing they thought about and just worked it out. But yeah. Okay. So what is the deal with all these derivatives? Now, since this network right here has these sine waves in it, right? So it's a neural network with sine waves as derivatives, as nonlinearities. What now? So we have a neural network. What now is the first derivative of that neural network, right, with respect to its input? So we have an input. Now what's the first derivative with respect to its input? And the cool thing about this is, what's the first derivative of a sine wave? It's, of course, a sine wave that's shifted. So it's a cosine, which is a sine wave that's simply phase shifted. And then the next derivative, again, is a shifted sine wave, and so on. So the derivative of a siren is a siren. And that does not hold for any of these other nonlinearities. So in ReLUs, it's the derivative of a ReLU network is like so if I take the derivative of this, it's like a constant 0 right here and then a constant 1 right here. And if I then take the derivative again, it's simply a constant 0 function, right? And all these other nonlinearities, their derivatives are different from themselves. And here, since we want to not only match a signal, but also the signal's derivatives, these property of this siren become in very, very, very handy. So how do you train a siren? We've already alluded to how you would do that in the kind of idea of matching an image, where you simply train the pixel values to the RGB values. But there's more that you can do with the sirens, given that given that their derivatives are also sirens. What you can do, so with the image part, we've basically neglected all of this. We simply said we want to find a relationship between the input x and the output, like this. What we can also do is we can say, no. We want to find a relationship between the input and its first derivative, and not even have this as part of the, let's say, of the loss function. And then we can see what comes out. So that's what they do. Can I find it? That's what they do right here. Okay, so here you see the ground truth image, and this is its gradients, and this is its Laplacian. Okay, now we've already seen that we can fit the image itself, but what if we just fit the first derivative? So we simply input this thing right here. We input this into the siren. We do the same thing, right? The siren is now, it maps x and y to RGB, but our loss function isn't going to be mapping x and y to RGB. Our loss function is going to depend on the gradient of that. So our loss function is going to be something like the gradient of the image, let's call the image I, minus the gradient of that function that maps x of this function right here. Okay, because we have these auto differentiation tools right now, we can easily make this into a loss function. So here we are looking for the function whose gradient matches the gradient of the image, right? Now, again, you can say, why can't we just match the image itself? And valid point, but it's not about why can't we just, it's about demonstrating the power of these networks. So if you only match the gradients, right, what you'll find is if you then look at the function, right, you still find the function. You don't find the gradient. You still train the function. You still train the weights of the function itself, but the loss function depends on the gradient of that function. If you do that, you'll find that if you then look at the function, again, you can ask the function to produce the image by simply cycling over each of the coordinates. You'll find that, look at that, just by matching the gradient, you'll match the image itself pretty well, right? And that's pretty cool. Now, of course, you're not going to match the RGB values. This is a grayscale image, and there's kind of a reason for that, because since the gradient loses like constant bias information. So what if you'd match an RGB image, I'm going to guess you're going to have like very much color distortions, and here what you're going to have in this case is just distortions in luminosity. Like if you know that if you have a function, if you have the derivative of a function and you will want to find the function itself and you integrate, then the solution is always an entire space of functions, because you will integrate this thing right here, and so with the whatever its input is, and you will have to add a constant, and you don't know what the constant was in the original function, because when you derive the function, the constant drops away. So similarly here, what we'd expect is that the image that we're getting back will be faithful with respect to like its borders, right? Since we're matching the gradient, and the gradient is basically an edge detector, will match the sort of edge information of the picture, which you can clearly see. But what we would expect is some difference in overall luminosity. And I don't even know how they exactly did this, because they now have to choose a constant to add. Maybe they just chose it in some way, or maybe they just let the network do. But this is, still pretty impressive. You can see there's some detail missing, but not much. And the exact same thing you can do for matching the second derivative. So now you match the Laplacian of the image. And remember, in the ReLU networks, they don't even have a Laplacian. It's a constant. So this is something you could never do. And you can see that the outcoming image is still pretty good, right? This is now missing the constant luminosity in the first and second derivative. Sorry, in the 0th and first derivative, and still the information is the reconstruction is pretty good. All right, so this demonstrates kind of the power of these networks. Again, we're not having our data set, our entire data set is just this image. So if we fit something, then this thing right here is our entire data set. There's no big data set and this is a test sample. Like this is the data set and the test sample at the same. I guess you can consider the Laplacian here the data set, and then the actual image is the test sample, like the label or something like this. So what does that buy you? Here is a thing you can do. If you want to mix two images, what do? So if you want to mix this and this, what you could do is linearly interpolate. But that would be not very cool, because right here you have a lot of very bright pixels, which probably have like values of 1. And here you'd have the dark pixels, which probably have values like more close to 0. And if you simply mix them, if you simply add them together and divide by 2, then you'd kind of get a wash of the two. And similarly here, you kind of wash out the bare, because you'd have some pixel values here that would come over. And generally not a good idea to mix images like this. Now, with GANs we can do this, but we have to have like a training data set and so on. Here, what we'll say is we'll simply say, we'll take the gradient of this, and we'll take the gradient of this, and then we'll add the two gradient maps. Now, what this does is that, as you can see right here on the left, is the composite gradients. And what this does is, right here in the sky, there is no gradient information in this image, because it's just a flat patch of sky, right? And maybe down here, there's not that much gradient information. There is a bit, right? But not here. So that's where this bare head is. And if you want to mix images, like, it can be a good idea to mix their gradients, because generally the information in an image is where the gradients are. So what we would expect the gradient to represent, the gradient would carry over this portion. It would maybe carry over a bit of this portion. It would carry over this portion and this portion. So everything where the signal is not flat. So here you can see the composite gradient. And if we fit, again, we fit our function such that the gradient of the function that we fit matches this mixed gradient right here, then this is the gradient of the function that we match, and this is the actual function. And you can see pretty good, right? It basically mixed everywhere where there was gradient. And this is now just reconstructed from this gradient. There is no, at least as I understand it, there is no pixel information carried over from either of those images. They're simply added to this gradient. The gradient is fit, and then the function is asked to output a pixel value at each location, and that's that. Okay, so this is just a simple, thing that you can play around with, but they do other more interesting things right here. For example, this representing shapes with signed distance functions. So if you go over the formulation, the actual formulation of their loss function, we haven't actually done this quite yet. It's here. It's very complicatedly stated, but ultimately what this means is, so a component right here are these CM, which are constraints. So this loss function operates on these constraints, and the constraints are across a of x, which basically is just x. It's kind of anything depending on the input itself, then the output of the function, the gradient of the output of the function, the second derivative, third derivative, and so on. So these sirens can fit anything that you can formulate as a set of constraints that relate the input of the function right here to its output or any of its derivatives. And we've already seen that if we fit an image, our only constraint is that these things match right here with the original image, that the coordinates are mapped to the RGB values. Then when we match the gradients, we don't care about this. We only care about the relation between this, and so on. So the loss function is literally just over the entire signal space, which in our case was over the entire image. We want these constraints to hold, or to be as small as possible. Right? The constraints are always formulated such that if they are fulfilled, they equal 0. And so for example, the L2 loss between the RGB values of the true image and the RGB values that you fit, the L2 loss would be a constraint like this. And of course, the more differentiable you make it, the easier this network has at fitting it, right? So that's why there's this norm right here. But it's not that complicated. It simply says whatever you can formulate as a constraint on relating the inputs to the outputs or any of the derivatives of this implicit representation, that is the loss function. All right, so the next interesting thing we can do, as I said, is representing shapes with signed distance functions. So we're going to go slowly, and this is, it's not that hard. Inspired by recent work on shape representation with differentiable signed distance functions, SDFs, we fit SDFs directly on oriented point clouds using both ReLU-based implicit neural representations and Sirens. Okay, so what is an SDF, a signed distance function? That's pretty easy. A signed distance function is simply a distance function with a sign. Like, wow. So if you have and it's usually done if you have like a boundary somewhere between things, then of course any point here has a distance to the boundary. But if you have a signed distance function, it simply means that each point also has a sign in front of it. And that means all the things on one side of the boundary maybe have a plus, and all the things on the other side maybe have a minus. So even though 2 points could be the same distance from the boundary, one is like +5 away and one is -5 away. And you can do this. This is useful, for example, when you fit point clouds, as they do in this example. So when they have point clouds, that's usually in 3D space, but if you have point clouds, you basically have points right here, and you know that the points should represent some kind of shape, maybe a wall, or so they have these room interiors, as you can see right here. So this is a 3D scene, but you only have a point cloud of the 3D scene. And what that means is that maybe you were in this room and you put up a laser scanner right here. Laser scanner, I have no clue how a laser scanner looks. And the laser scanner kind of shoots lasers at random locations and always measures the distance, right? And that's how you end up with a point cloud. So you'll end up with like a point cloud where in 3D space you know where the laser hit something. And a reasonable assumption to make, if you have like a dense sampling of this, is that you should be able to like connect those point clouds in some way to obtain the actual continuous shape of the thing that you measured. And this is what we're going to try to do with these sirens, right? To go from point clouds to shape by training an implicit representation. So we're going to train a neural network that represents this shape right here, basically by mapping coordinates to signed distance values. So whenever we ask the neural network, what at this location here, what's the signed distance? And it's going to tell us, oh, it's +5. Or at this location here, what's the signed distance? It's going to tell us, it's 0, right? So we're going to train a neural network to do that. And hello, yes, no, okay. So this is a bit more complicated. And since we have these awesome power of these sirens, we can also do more constraints. So we know, and this goes on, this amounts to solving a particular iconal boundary value problem that constrains the norm of spatial gradients to be 1 almost everywhere. So this iconal boundary value problem, this is a property of signed distance function, that the norm of the gradients with respect to the input is 1 almost everywhere. Almost everywhere means everywhere, I guess, except at the boundary itself where the distance is 0. Though I could be wrong. Note that ReLU networks are seemingly ideal for representing SDFs, as their gradients are locally constant and their second derivatives are 0. Adequate training procedure for working directly with point clouds were described in prior work. We fit a siren to an oriented point cloud using a loss of the form, and now we'll look at the loss. So the first thing you observe in the loss is that it is made of 3 different integrals, and that simply means they now partition the space right here. They partition it into 2 different regions, so to say. So maybe go here. No, can I zoom here? So the first region is going to be whatever is on the boundary itself, right? And that's basically wherever a point hit, right? Whenever you have a point or on the boundary itself, that's going to be your omega 0 is going to be that. And then all the other points right here are going to be part of your omega without the omega 0. So you're going to have different constraints for all of these things right here, for example. and I have to pay attention that I don't say anything wrong, you'll have this constraint of this gradient. My tablet, I need new. Maybe I'll start monetizing just so I can get a new tablet. Okay, so no, okay. This condition right here says that the gradient should be 1, and that's actually everywhere, right? So I was wrong that the gradient is only 1 outside the boundary. Then you can see right here, the last part is all the points that are not on the boundary, since our network maps any point in 3D space to a signed distance function. So most of these points aren't going to be on the boundary itself, even though in the mini batch where they train, they sample points on and off the boundary at equal rates, just to have the network train more stably. So this is a condition on all the points off of the boundary. And they say here, this function is this exponential function with alpha larger than 1. It penalizes off-surface points for creating SDF values close to 0. So this is simply a regularizer that says whenever I input coordinates that are far away from the boundary, from the surface, then there should be a large signed distance function. Like, it should not be close to 0 because it's away from a boundary, okay? And in practice, how you're going to train this is, if you have a point cloud, if your coordinates are far away from the next point, then this is going to be a high, this should be a high value, otherwise the network is penalized. So we have this condition right here on the gradients, which we know signed distance function should fulfill. We have this thing right here, which is a regularizer, basically telling points far away from our data that they should have a high distance function. And then we have this last thing right here, which is for all the points on the surface itself. Here's what we require. First of all, we require their value to be 0 or close to 0, right? This is the loss function, so we want to minimize this. And this is simply the output value. So the signed distance function of points on the surface, the things we actually measure, they should be 0, right? Because the signed distance function measures how far away from the surface you are. So this is pretty intuitive. But then also, this right here, it says that the gradient of the signed distance function and the normal vector of that point should align. And that basically means, and this is now, I think this is because we have an oriented point cloud, or no? Yes. So what we can do is we can kind of connect points next to each other and then calculate the normal vectors of that, right? And the network, if we ask the network, hey, what do you think about this position right here? The network should tell us, first of all, the signed distance function should be 0 because it's on the boundary. Second of all, the norm of the gradient of the signed distance function at that point should be 1 because that's a property of signed distance function. And third, and that's the thing right now, the gradient of the signed distance function should align with this normal vector, right? And that's pretty intuitive because you want the signed distance function to increase in value. The gradient basically tells you where the highest increase in value of the function is. You want it to increase along the normal direction and not along any other direction, right? So that's a pretty good constraint to have. So you can see right here, I mean, you don't really have to understand exactly about signed distance functions and so on, but these Sirens are pretty good at capturing all of these different constraints. And this was a point, on the surface. Points off the surface, you additionally say, hey, you should have a pretty high value, and actually not a 0 value, but a pretty high value, right? So, and again, we only fit one particular scene. We only ever fit one scene with an entire network. So the entire neural network, this whole structure right here, everything is captured by this neural network that we train on the point cloud. And you can see that if you use a ReLU, what you'll get is super wobbly, because even if you train the ReLU with the same loss function, these constraints on the gradients, they're just not going to work out with the ReLU, because the gradients are like constant and discontinuous, right? Whereas the Siren can basically fulfill all of these constraints on the different parts, like on the values and on the gradients of the loss function. And they have another example right here where they fit this shape. Yeah, so you see all the details are preserved way better, where the ReLUs, they'll simply kind of flatten over everything and make it wobbly. All right, so I hope this sort of made sense, and we'll go to the last thing right now. It is restarting. I wanted to show you the website right here they have for this. It's a pretty cool website to go along with it, and as you can see right here, they have all these samples that they have in the paper, but also in animated format. As you can see right here, this is the fitting process, the learning process of how you represent these images. So as I said, you want to fit these functions to the ground truth, and that happens in steps. So this is very much like you would learn a deep learning functions. I think they use the Adam optimizer. It's just that the data set now all comes from this one ground truth image, and you can see that the Siren network on the right pretty quickly zeroes in on the image and then gets the details subsequently right. They also represent audio with this, and you can watch that. They represent video. Compare that to ReLU representations. Then here, solving the Poisson equation is where you only fit the gradients or the Laplacian of an image and still get out the good image. That's pretty cool. And here you can see that you can actually play around with these things. So you can click on them and look at this learned thing. So on the left, you can see what the Siren network learned, and so I'll scroll down here a bit. And on the right is a ReLU representation of the same thing. So this is the same network with the same objective. It just has ReLUs instead of sine waves as activation functions. So you can see how much of a difference that makes right here. And the middle is a ReLU with the positional encodings. Still not good, right? The only thing right here that you have to think of, if you look at how big these Sirens are, how many parameters they have, they're about at the order of magnitude of how many pixels there are in the image. So it's certainly a cool method, but it's not like the implicit representation here is very, very well at generalizing, though it would be very cool to see what happens outside, right? Because now you can input any XY coordinate. So technically you could continue the picture to the bottom and just see what the Siren thinks should be here at the bottom. So all of these things would be pretty cool to actually experiment with, and they have the code available to do that. And you can see the fitting process of the Helmholtz equation right here, and related projects. Pretty cool website. I definitely invite you to check it out. And let's go back to the paper. And we're back, and my tablet crashed, and let's continue. So they're now going on to use Sirens in order to solve PDEs. And so in physics, often you have these problems where you are given an equation, but the equation doesn't necessarily involve a function itself, but only involves derivatives of that function, or relates derivatives to the function, and so on. So one example here is this Helmholtz equation that's given as this, where I think the f is a known function, but this is the wave field you wanna get. You want to figure out, which is unknown, and then this h m is including, for example, this right here, which is the Laplace operator. So you're given the relation between the function and a Laplace operator of the wave that you want to find out, and your task is to recover the wave. Now, I don't want to go very much into this right here, but what you can do is basically you can measure, you can have a room and you can have measurements of the wave or of its derivatives and so on, and then you kind of calculate backwards from the measurements to what the actual wave was. And these Sirens turn out to be very, very good at things like this. And I guess that's in this solving for the wave field things. But essentially what this amounts to is a numerical solution of these partial differential equations in physics using these Sirens. And that's pretty cool. And the last thing they do is, and this gets back to a more of the machine learning context, where they say learning a space of implicit functions. So now they go ahead and say, yeah, so we can represent images in terms of these functions, right? But each image is basically its own function. So each image is basically an optimization, a fitting problem. Can we somehow learn functions of functions? So this comes now back to more of a machine learning context, where you say, so I have a network right here that I have a network that gives me the parameters of the Siren. So this right here is okay, let's go to an example. In this example, what you'll have is you'll have an image like this one where a few pixels are masked. Actually, most of the pixels are masked. And you want to put this into a CNN, and the CNN should output the parameters of the Siren network. So the parameters, because the Siren network, given its parameters, is the image itself. So that's the Siren, I said Siren network. The Siren is the image if you know its parameters, right? So here you train a CNN to give you the parameters of the Siren. That's almost the same as training a CNN to give you the image directly. But again, we don't want to have the explicit representation of an image. We want to have the implicit representation such that it's continuous and we can manipulate it and so on. So the CNN is now trained on a data set. So you take CFAR10 and you construct a whole bunch of images with only kind of 100 pixels remaining. And then you train a CNN to give you the parameters of the Siren that would reconstruct the ground truth, right? And then you can test that on the test image. And you can see right here, the results are pretty good. So these are test samples. These are now images that were not seen during training of this CNN. And therefore, the outcoming Siren also hasn't seen that image. The Siren is simply parameterized by the CNN. And you can see this works pretty well. So if you only have 10 pixels, you already get something out of it, right? And if you have 100 pixel, you already get fairly close to the ground truth right here. Now, this is not GAN quality images, of course, but it's pretty impressive to see that an implicit parameterization, an implicit representation of the images can be so powerful, right? Yeah, so this is a pretty cool thing. And again, it's better than, it's kind of more back to the machine learning framework that you're used to, because there's a train and a test data set. And now the only thing is that the output is a function given by its parameters and not the actual pixel values. Okay, so let's look at the broader impact statement. The proposed Siren representation enables accurate representations of natural signals, such as images, audio, and video in a deep learning framework. This may be an enabler for downstream tasks involving such signals, such as classification for images or speech-to-text systems for audio. Such applications may be leveraged for both positive and negative ends. Siren may in the future further enable novel approaches to the generation of such signals. This has potential for misuse in impersonating actors without their consent. For an in-depth discussion of so-called deepfakes, we refer the reader to a recent review article on neural rendering. This has like no perplexity at all. Like, is anyone benefited by this? Seriously? Okay. But at least we made the authors think of the consequences of their research. So I invite you to check out this paper. Maybe with this right now, you can follow a bit better what happens here. This is a different paradigm of research. It's a cool paradigm. It's away from your usual machine learning framework. And yeah, so I'm excited what happens next in this. I also invite you to check out the websites. They have lots of videos and goodies and so on. And with that, bye-bye.